Okay, hello and welcome to the ATAR Notes lectures for 2024 July for Mathematics Extension 2. Welcome everyone. Just a bit about us. ATAR Notes has heaps of free resources, heaps of study notes, lectures, discussions, videos as well, newsletters at ATAR Calculator as well, articles and heaps more. So feel free to check out the ATAR Notes website. Heaps of free resources, heaps of really useful resources. I used them personally when I was in the HSC, doing the HSC, so highly recommend them as well. And ATAR Notes Plus, thousands of study resources as well. On having the ATAR Notes topic tests, the course notes as well. Heaps of resources in that sense as well. So yeah, let's get started. Mathematics Extension 2. A bit about me just before we start. I'm Rohan. I'm currently completing civil engineering and physics at UNSW. Graduated in 2022 with an ATAR of 98.3. The subjects I did were Mathematics Extension 1, Extension 2, Physics, Chemistry, Design, Tech, and English. And yeah, I was a student here at the tutor program. Now I'm a tutor. So yeah, I'm enjoying my courses. Really found all the HSC content really useful and helpful. Yeah. So in terms of what we're going to do today, we're going to jump into some mechanics. I know some schools tend to leave mechanics towards the end, and majority of schools do that. And so what we're going to do is try and get a head start if you guys haven't already started, or a bit of revision of the mechanics topic. Try and do a crash course into it. Try and run through all the topics, cover some examples. So yeah, let's get started. First, we're going to start with some motion without resistance. So motion without resistance is one of the specific types of motion that is covered in the HSC Mathematics Extension 2 syllabus. It used to be actually something that was in the HSC Extension 1 syllabus. Now it's in the Extension 2 syllabus, but it's a solid foundation because a lot of the equations that you use for motion without resistance is also applicable to motion with resistance. So yeah. Now, a bit of revision, obviously you would have seen this stuff in potentially year 11 or even earlier. Displacement, the displacement function is given in terms of x, velocity is v, and it's the time derivative of the position or displacement, and it's sometimes denoted as x dot, and dots, again, are often utilized to demonstrate the time derivative of a function. Now, acceleration is the rate of change in velocity, that is, how fast you're becoming faster, if that makes sense. So it's pretty much, when you think about acceleration, you think about like sort of the accelerator in a car. You're increasing your velocity. You're going from say 0 kilometers per hour to 60, 80, 90, 110, whatever, right? So acceleration is getting faster. Velocity is a measure of how fast you're going. Displacement or position is where you are. And acceleration is the time derivative of velocity, right? And because we know that velocity is a time derivative of position, we can also express acceleration as a second derivative of position with respect to time. And so it's denoted as x double dot. Okay, so you can see that the expressions for x of t, velocity, v of t, and a of t all clearly define functions of time. Right? That is, they are dependent on time, and you see a t in the formula for them. However, sometimes it's more useful to express acceleration in terms of displacement, x, or in terms of velocity, v, rather than in terms of time. Now, the reason why we heavily emphasize acceleration is because that's sort of our starting point in a lot of questions, and the reason for that is Newton's second law. So Newton's second law, when we analyze the forces on a system, right, we can say, okay, this is the net force, this is the mass of the object, hence the acceleration must be so and so. And we can do that in different dimensions, so we can have that a two-dimensional, three-dimensional case. For the HSC, usually you're dealing with two-dimensional cases at maximum. One-dimensional cases for motion without resistance and resisted motion and simple harmonic motion. Projectile motion is the case where you're going to start dealing with two dimensions. But yeah, we'll get to that in a bit. But yeah, so sometimes it's more useful to express it in terms of velocity rather than velocity or position rather than time. Now, if v of x specifies a velocity function of x, then we can use the chain rule of differentiation to calculate acceleration. So we're going to say that dv dt, right, is equal to dv dx times dx dt. Now, you might be asking why we're doing that, but it will become obvious in a second. But as to why that's true, It's just an application of the chain rule. Now remember, chain rule sort of looks like a bit like fractions, right? A bit like the fractions cancelling each other. Now that's not exactly the case, but we can sort of pretend it is. So you can sort of think about the dx's cancelling each other, and so we still end up with the same dv on dt expression. So we can say dv on dt is dv on dx times dx on dt. Okay. So dv dt is therefore dv dx times v. Now, the reason we can say that is, where have we seen dx dt before? Well, that's just our definition. If you go back to this slide here, that's just our definition of velocity. And therefore, we can say that dv dt equals dv dx times v. We just replace that dx dt with v. Okay, so that is one form of acceleration. So we can say x double dot is our acceleration, or dv dt is equal to, now usually they just switched around in order, so v dv dx, that's one of the forms of acceleration. That involves v's and x's. Now there is another expression that we can come up with, which also includes v's and x's. You might be interested in like why that's useful, but we'll potentially cover a few examples in which we're going to have to use that expression, and that's going to hopefully make it a bit more obvious in terms of why we do this thing. So we get dv dt equals dv dx times d dv half v squared. Now you might be wondering where that came from, but if you just evaluate this derivative here, that's the derivative of v squared on 2, or if you use just power rule there, that's just going to be v, right? And so all we're doing is we're replacing that v with a derivative expression equivalent to it. Now, that seems like we're overcomplicating things, but here's where the chain rule comes in again. You see we have a dv here and a dv here. That means that they sort of cancel. Now, again, not exactly cancellation. It's just a result of the chain rule, but we can sort of treat it like fractions. And so we can say dv dt equals d by dx of v squared on 2. Now, that's our second form of acceleration. So we get x double dot equals dv dt. Oops. dv dt. Let me just clear that out. So dv dt equals to v dv dx. That's one form, and that's also equivalent to d by dx of v squared on 2. So that we have our two forms of acceleration. Now, we have to be careful in terms of picking which form is it applicable to each question. So yeah, these are our different forms of acceleration. We've got dv dt, just the rate of change in velocity. And because the velocity is the rate of change in position, we can express the acceleration as a second derivative of position with respect to time squared, with respect to time, so we get that. And then we came up with our v dv dx expression, which is just an application of chain rule, right? And then we came up with this expression here, which involved coming up with an equivalent expression for velocity as a derivative, and then applying chain rule. So these are our four forms of acceleration. Now the first one, the third one, and the fourth one are the most commonly used ones. Now the second one's also used, but that involves, say, if you start off with an acceleration as a function of time and you have to integrate it twice, then you can end up with a position as a function of time. That's still used, but in terms of the HSC Extension 2 syllabus, the first, the third, and the fourth ones are used the most. Not to say that the second one isn't used, but it's just the way most questions like to do it. Okay, jumping into picking the right equation. Okay, so given acceleration is a function of so the forms you use in a particular problem will depend on the form of the equation that defines acceleration. So given that the acceleration is a function of time, we use dv dt, or d squared x, and that should be dt squared, in order to come up with a velocity or a position expression, right? So if we've got time involved, so that is acceleration is purely a function of time. So like say 3t squared plus 4, clearly 3t squared plus 4 is purely a function of time, hence we can use dv dt, or we can use d squared x dt squared. Okay, and so is going to give us a velocity as a function of time expression or a position as a function of time expression. What if we have an acceleration as a function of position? What if, the further away we are from the origin, the greater the acceleration gets? And we'll come across a very specific example of that in simple harmonic motion. But what if that is the case? What if the acceleration is a function of position only? Then in that case we would use d dx of v squared on 2. Now, if acceleration is a function of velocity, which again we'll come across in resisted motion, right? So for example, when we're talking about resistance, just a bit of a peek ahead. If we're talking about resistance, right, particularly air resistance, the faster you go, the greater the acceleration, the greater the sort of resistance becomes, right? And therefore the greater the force becomes. And so in that case, it's actually proportional to the velocity squared. If we're talking about just aerodynamic drag. And so because it's proportional to the velocity squared, our final force function is most likely proportional to the velocity. And in that case, we use dv dt if the initial conditions are in terms of t and v. So that is, if we say initially the particle is at rest, or if we say something along the lines of if the at t equals 5 seconds, the particle is traveling at 10 meters per second. If we have some initial conditions in terms of t and v, then we use dv dt. Otherwise, if we have initial conditions in terms of x and v, it should be a v, in terms of x and v, then we would use v dv dx. So that is something like initially if the particle we say is at the origin, so at x equals 0, v equals 0, so initially when the particle is at the origin, it is at rest or something like that, then we would use v dv dx. Otherwise, if it's in terms of t and v, we use dv dt. And it seems a bit theoretical when we say it this way, but hopefully a few examples will clear that up. And yeah, let's start with our first example. This is actually pulled from the extension 1 HSC from 2017, question 12D. If you go to past papers from Maths Extension 1 before 2020, you'll see that some of them involve a few of these v dv dx, dy dx, v squared onto dv dt questions, which have now been moved into the Extension 2 syllabus. You might find them sort of easier compared to, the actual HSC Extension 2 type questions, but they're still worth practicing because it helps you sort of practice the use of picking the right expression and using the right expression. So yeah, let's do this one. So, open up OneNote. And that should be visible. Okay, so let's start with our expression. We're given that t equals to 4 minus e to the minus 2x, right? And we're asked to find the expression for acceleration, that is x double dot. Okay, so we have t and x, right? And what does that mean? We're probably going to have to use dx dt, right, in order to get a velocity expression. Because to get from position to acceleration, you either have to differentiate position twice to get acceleration, or you have to get to velocity and then use some of the other forms. So to get the position expression, now we have an option of trying to rearrange this and get x equals so-and-so in terms of t. But there turns out to be a more efficient way, and that is to use one of the rules for reciprocating derivatives. Again, treating derivatives a bit like fractions, but again, it's a result of the chain rule. So if we take the derivative of t with respect to x, which is the actual sort of flipped version of velocity, we get the derivative of 4 is just 0, derivative of minus e to the minus 2x, if we bring the negative 2 down, is 2e to the minus 2x, right? And from there, we want a velocity expression, and if we want a velocity expression, that means that we're going to have to use, sort of reciprocate both sides. And so what we can do is we can say dx dt is equal to 1/2 e to the power of 2x. Now, because if we reciprocate a negative 2x, it's going to be to the power of positive 2x. Okay, so that gives us a velocity expression. V equals to v equals to 1/2 e to the 2x. Okay, now we're at an interesting point. We have a velocity and position relationship. So that means that we're probably not going to have to differentiate with respect to time again, because we have no t expressions, right? We could potentially try and use v dv dx, but in this case, I think what's better is going to be, now either way, I think it should either way work, but what I'm going to do is I'm going to square it. Is v squared is 1/4 e to the power of 4x, and divide that by 2. Now remember, our acceleration form was d by dx of v squared on 2, so we want to try and force it into that form. So we get v squared on 2 equals to 1/8 e to the power of 2x. Sorry, 4x. And then we can take the position derivative. So we get d dx of v squared on 2 equals 2. So if we take the position derivative of that, the 4 comes down, so we get 1/2 e to the power of 4x. And remember, dx of v squared on 2, that is our acceleration expression, so we can say x double dot, which is the second derivative of position with respect to time, is 1/2 e to the power of 4x. Pretty easy, pretty straightforward, just using one of those forms. Now at this point, if we use dv dx, then we should pretty much end up with the same expression, right? So if we use dv dx at this point, that's going to be 1/2 times, so 1/2 divided by 2, which is 1/4 e to the power of 2x. And then v dv dx is dv dx sorry, that should be 1/2. Yep, so 1/2 times there we go, that's where it went wrong. If you take the derivative of e to the 2x, half e to the 2x, that's just e to the 2x, right? And so that's just going to be, if we multiply the two quantities, v dv dx, that's going to be 1/2 e to the 4x. So same result, you could go either way, really doesn't matter in this case, they're both about the same amount of work. So, yeah. But sometimes one will be quite obviously a lot more work or a lot less work than the other. So it's a matter of picking and choosing which one's the most appropriate in each case. Okay, moving on to the next question. We have a particle is moving horizontally. Initially the particle is at the origin, right? O, moving with a velocity of 1 meters per second. The acceleration is given x double dot equals x minus 1, where x is displacement, is its displacement at time t. Now at that moment, you should stop there and say, okay, we've got acceleration as a function of position, right? And so that means that we're going to have to use potentially v dv dx or d by dx of v squared on 2. But if we're eventually going to try and find a position or a velocity expression at some point. And we also have an initial condition, that is initially the particle is at the origin, that is position, with velocity 1 meters per second. So we have a position-velocity relationship in terms of an initial condition. Okay, part 1 says show that the velocity of the particle is given by x dot equals 1 minus x. Okay, so x dot is just our velocity, right? So we want to try and show that that's equal to 1 minus x if x double dot equals x minus 1. So let's do that. So we know that, let's just give ourselves some room. Yep. So we know that x double dot So we know that x double dot equals to x minus 1. And we're looking for a velocity position relationship, right? And so let's use this time d dx of v squared on 2. Let's express our acceleration in that form. And the reason we do it in that form is because we have on the right hand side a function that is purely a function of position. And in that case, we can go ahead and integrate with respect to position, right? So we can say v squared on 2. If we integrate the left hand side, it's just going to be v squared on 2, right? V squared on 2 equals to the integral of x minus 1 dx. And so here we're going to end up with the integral of x is just going to be x squared on 2. And the integral of 1 is just going to be x. Now remember, whenever we have an indefinite integral, we're going to end up with a constant, c1. When we integrate the left-hand side, we do theoretically get another constant, but because we have two indefinite integrals on both sides, we can sort of clump them into one constant and leave that on the right-hand side. So we end up with the expression v squared on 2 equals to x squared on 2 minus 2x, sorry, minus x, sorry, plus c1. Okay, and we can go through and multiply through by 2, and we end up with v squared equals x squared minus 2x plus, I'm going to leave it as c1. Now the reason I can do that is because it doesn't really matter what I call it as long as we end up with the right number at the end. So plus, or we can even call it c1 dash if we'd like. Now, how do we evaluate c1 dash? Because obviously in our final expression we don't have a c1 or some constant in there. How do we evaluate that? Well, that's where our initial condition comes in. We know that when t equals 0, that is initially, x equals 0, and our velocity equals 1, because we're told that initially the particle is at the origin, and its velocity is 1 meters per second. So let's go ahead and plug that in. So we get 1 squared on the right, so just 1. 1 equals to x squared, so 0 minus 2 times 0, which is 0, c1 dash. So clearly, therefore, we conclude that c1 dash equals 1. What does that mean in terms of the equation? So what does that give us in our final equation? So we get v squared equals x squared minus 2x plus 1. We're not quite there yet, but the reason we're not, but if we look back at the expression that we're looking for x dot equals 1 minus x. How do we end up with a 1 minus x from this expression here? Well, the way we end up with that is by using a bit of a clever trick, and that is to use some factorization. You have to keep your eye out for potential perfect squares. So in this case, x squared minus 2x plus 1, that's a perfect square, and we can express it as x minus 1 squared. Now that, trying to sort of see that the moment you do these sort of questions is a bit tricky, but it just comes with practice. So yeah, you need to be able to sort of look through expressions, see some patterns, and see what's a perfect square, what's not. What can you do to get it into the form that we're looking for? Now we can go ahead and square root both sides, and if we square root both sides, we get so v equals to plus or minus x minus 1. Now we do definitely need the plus or minus there because we're taking the square root, and this quantity can either be positive or negative, right? X minus 1 can, like the value that we're taking the square root of when it comes out, or when we square this value, it can take positive or negative form when we square root it. And so if that's the case, we can say we need to look at one additional thing, right? And that is when x, well, additional thing in the sense that we've already looked at it, but we need to use that piece of information in order to figure out what, whether it's a plus or in the minus case. And that is, we use the initial condition again. This sort of question is a bit rare in the sense that it's hard to find questions where you're going to have to use the same initial condition twice. But clearly it still does exist. So we get v equals to 1 at x equals 0. So we get plus or minus 0 minus 1 equals positive 1. Well, that clearly means we're going to take the negative case, right? So that means if we want 1 coming out of that expression, we're going to take the negative case. So we get v equals to negative x minus 1. Or if we sort of redistribute the minus sign, we end up with 1 minus x. And that was the expression we're looking for. So we end up with v, or x dot, either way, is equal to 1 minus x. And so we're done with part 1. Part 2 says find an expression for x as a function of t. Okay, so we have a velocity in terms of position. This is a good platform to find position as a function of time. Why? Because we can express velocity, so v equals 1 minus x, as dx dt. And here's where we do the little reciprocating trick, right? We can go ahead and flip both sides, sort of like fractions, but again, not because they're fractions, but because of a result of the chain rule. We end up with dt dx equals to 1 over 1 minus x. Sorry about that. 1 minus x. And so now we can go ahead and integrate both sides with respect to x, and so we end up with dt is equal to the integral. So let's put an integral there. So we end up with integral of dt with respect to x. If we separate variables, is 1 over 1 minus x dx. Now, the integral of that is going to be negative ln 1 minus x, because if we take the derivative of 1 minus x, that's minus 1, and negative out the front cancels it, and so we get the f dash x over f of x, and that's clearly an ln, plus a constant here, because again, it's an indefinite integral, so I'm going to call that c2, and that's t. Okay, so we're at this stage where we've got t, x, and the c2. We need to try and get rid of the c2, and that's again where we rely on the initial condition. This time not in terms of velocity and position, this time in terms of position and time. So we're told that when t equals 0, that is, another way of saying that is initially, t equals 0, x equals 0. The particle is at the origin. And so if we sub that in, we end up with 0 equals to minus ln 1 minus 0, which is just 1, plus c2. ln 1, that's 0. And so that concludes that c2 must also be 0. And so our expression for for time is minus ln 1 minus x. Because the c2 just drops out because it's 0. Once we've gotten that, we're looking for position as a function of time. So we're not there quite yet. We need to do a bit of rearranging. So if we do that, we get minus t equals to ln 1 minus x. And we take the exponential of both sides, so we get exponentiate both sides, is a better way of saying it. E to the minus t is 1 minus x. And so if we sort of swap the x and the e to the minus t, we end up with x as a function of time is equal to 1 minus e to the minus t. And so we're done. So we've come up with an expression for position as a function of time. X as a function of t is 1 minus e to the minus t. So we're done. Almost done, sorry. Part 3 says find the limiting position of the particle. So because we know that x equals to 1 minus e to the minus t, to answer part 3, whenever it says limiting something, whether it be position, velocity, acceleration, and limiting velocity is something that's sometimes called terminal velocity. We'll get to that in the resisted motion section. But in terms of whenever it says a limiting position, that usually means that we're limiting anything. That usually means that we're sending t to infinity. We're looking at what happens eventually, or as time goes to infinity. So another way they'll say that is find the eventual position of the particle, or eventually what position does the particle approach. Then in that case, we set t go to infinity, or we take the limit as t goes to infinity if we want to take it in the sort of stricter mathematical sense. If we take the limit as t goes to infinity, we get e to the power of some really large number effectively, and so e to the power of negative a really large number, and so that approaches 0, and so we end up with x approaching 1. So the limiting position, maybe I'll call it xl, is going to be 1. Okay. Now let's move on. We've got a particle starts at the origin with velocity 1 and acceleration given by a equals v squared plus v, and we're asked to find we're asked to find expression for x, the displacement of the particle in terms of v. Okay, so we start with acceleration. So acceleration equals v squared plus v, and so we start with v dv dx, right? And the reason we know that we need to jump to that is because clearly we have velocities on the right hand side, but not only that, we've got no positions involved. Otherwise, we could start thinking about using ddx on v squared on 2, right? But here, whenever you use ddx on v squared on 2, that usually means that your next step is to integrate with respect to position, but there's no positions involved at this point, and so we need to do a bit of manipulation first, and so we're going to divide through by the velocity on both sides. So we get dv dx equals to v plus 1, and we can flip both sides again because of chain rule. Dx dv equals to 1 on v plus 1, or 1 plus v, either way. And from there we can go ahead and integrate. So you get x equals to the integral of 1 on v plus 1 dv. And so that's just a straightforward ln function, right? Because if we take the derivative of v plus 1, that's just 1, and that's what we have on top. So we have f dash v over f of v, and so we have ln 1 plus v plus c1, because again, indefinite integral means we have a constant, and so we have a position in terms of v. Okay. Our final expression shouldn't involve constants unless they specifically say so, at least for the HSC level. So we have that. How do we evaluate the constant? Well, we need to look back at the question, look for some sort of initial condition or some point along the path or something like that. And clearly at the beginning of the question, they've said a particle starts at the origin, so t equals 0, x equals 0, with velocity 1, right? So t equals 0, x equals 0, v equals 1. We don't have a time in this, so we can use our x equals 0, v equals 1 expression. So when x equals 0, v equals to 1, substituting that in, we end up with 0 equals to ln 1 plus 1, which is 2, plus c1, right? And so c1 is just minus ln 2. Easy as that. Okay. And so our expression for position then becomes ln v plus 1 minus ln 2. And there we have it. X as a function of, so we're done. For 3 marks, that's not bad, I would say. We had, 4 lines of working at maximum, or 4 or 5. Not too bad. 3 marks, fairly easy marks, I would say. And this one's actually taken from an extension 2 paper. Okay, so that was motion without resistance. You'll see that eventually, as we come to the topics, that a lot of the equations, or pretty much all the equations that we talk about there, is pretty much applicable to the extent the resisted motion questions, the simple harmonic motion questions, and the projectile motion questions. And so, like, being familiar with them is very important, and obviously you get more practice at doing them as you do further topics as well. So yeah, let's jump into some simple harmonic motion. Now, simple harmonic motion is defined as it's not necessarily has to be like a physical particle, right? It's just anything that exhibits periodic motion. Now, a lot of things in the world is periodic, right? Water waves, any type of wave, pretty much sound waves, electromagnetic waves. A lot of that stuff is simple harmonic motion in the sense that it can be modeled with a sine or cosine function, or a sinusoidal function, or a linear combination of both if you want to. But the simple harmonic motion that is quite often talked about in the HSC is just like a physical sort of simple harmonic motion. But yeah, a lot of things in the world are simple harmonic. You know, engine cycles, heartbeats, a lot of things. And turns out sine and cosine are really versatile in the sense that you can break down any function into them. And so that's pretty cool as well. So having a good model of sine and cos can quite often translate to being able to use that for more complex signals and things like that. But that's going off on a tangent. So here we have 2 models. We have x equals a cos nt plus alpha plus c, and x equals a sine nt plus beta plus c. We'll talk about each one in detail, but bit of terminology. C corresponds to the center of motion. A is the amplitude. 2 pi on n, that is the n that's attached to the t on both of them, that dictates the period of motion. The quantities nt plus alpha plus and nt plus beta are called the phase of motion. That's just talking about, and particularly the alpha and beta, what they do is they talk about what if we're modeling 2 events simultaneously, right? And we start one later than the other, or we start both simultaneously, or we start the second one much earlier than the first one, obviously they're not going to be in phase, right? Or if we're using 2 simple harmonic pendulums, but one's got a shorter length, right? And so even though we start them at different positions, we're going to end up with different alpha and beta. They're related to the phase of motion. So each angle, alpha or beta, is called the initial phase. So, like I said, many things exhibit repeated patterns or oscillations. So examples include heart beatings, lungs breathing, engine motion, vibrations. Very important when you're talking about structures and things. Vibrations when we're talking about frequencies that sort of resonate and amplify very significantly, you have to be careful in terms of what frequencies do that, particularly for certain types of structures. Waves on the beach, tides of the ocean, phases of the moon, all these things are simple harmonic. That is, they repeat in a periodic cycle, in a well-defined periodic cycle. And the mathematics behind each of these examples is extremely complicated, but each one can be based on oscillations observed in the graphs of sine and cosine functions. In the real world, when talking about oscillations, right, even suspension systems can quite often be modeled with oscillations, or to a certain extent, damped oscillations. But in essence, they involve sine and cosine and are built up on a basic simple harmonic motion model. So the graph of x equals sine of t and x equals cosine of t should be not cos. Cos of t is called sinusoidal. So we've got amplitude is, and again, on terminology, if we graph that displacement, so x as a function of time, the height of the peaks from the center is called the amplitude. The period is the time between 2 peaks or 2 troughs, or sort of the time required to complete one full cycle. And that's the that's just a few basic terminologies. We'll come to more of them in a second. But whenever the graph of displacement x versus time t for a particular motion is sinusoidal, that motion is called simple harmonic motion, or SHM for short. And the equations are often written as, like we mentioned before, x equals a cos nt plus alpha plus t, or x equals a sine nt plus beta plus c. But like I mentioned, you can also have a linear combination of them, so x equals a cos nt plus b sine nt. Now, that is less common, in at least for the HSC syllabus, but effectively, if you're looking at the auxiliary angle form, the top two are equivalent to the bottom two. It's just, instead of having an alpha or beta, we're talking about two separate cos and sine functions, but you can sort of combine them using auxiliary angle form and turn them into the top ones. Okay, so here, when we're talking about the value, that should not point to the n, that should be pointing to the a, sorry. So that's that one, that one's that one. It looks like Slides has done something. And C. Okay, so the value a is the amplitude, the motion because amplitude of the motion because waves move away from the center by a. So again, if this was our graph, our amplitude is just this distance here from the center to the peak. Now, if the center is shifted up or down, it's still the distance from the center to the peak, not necessarily from 0 to the peak. And so that's going to be a. So what that a does is that defines where the limits of that motion is. So if you're thinking about, say, this is a very common example, or a sort of stock standard way of explaining things. It's a block on a spring resting on a surface, and it's moving back and forth, right? That is a very stock standard example of simple harmonic motion, and if this is our center, the two extremums are c plus a. That's our maximum in that direction, and the maximum in this direction is going to be c minus a, right? So it's going to be oscillating between c plus a and c minus a always. It's never going to exceed those bounds. That's what the a does, and that's what the c does. C, again, is center of motion. That's our middle point, and that should be the average between our lowest point and our maximum point. Okay, and n, this value n that's attached to the t, that corresponds to the period. And this formula here is very important. The period is 2 pi divided by n. And this formula is not only applicable to extension to simple harmonic motion. Just whenever you're graphing these sort of things, one of the first things that you should look at is what is the period. And so to figure out the period from this equation, you take n and you divide by 2 pi. So if n is 2, the period is pi. If the n is pi, the period is 2, and you just put in the respective value of n into that formula, and that should give you the period. And remember, the period is the time required to complete one full cycle, or you could also look at it as the time between two peaks or two troughs. Okay. At any time t, the quantities nt plus beta and nt plus alpha are called the phases of the motion, as their values determine the location. So pretty much the thing inside the brackets, those are called the phases of motion. Those, depending on what the time is, sort of dictate where the particle is at some point in time. Alpha and beta are called the initial phase, as they determine the initial form, or sort of if one is launched from the center and one is launched from one of the extremum, clearly those two particles are going to have different equations of motion, and that's what the alpha and beta account for. Okay, moving on. So when we start with our displacement as x equals a sine nt plus alpha, we'll drop the c for now because it doesn't really do much other than dictate where the center is. Our velocity expression, if we take the time derivative, is just going to be a n cos nt plus alpha. Right? Just take the derivative with respect to t, and so the thing inside the brackets is just dependent on t with that linearly. And so taking the derivative of nt plus alpha is just n, stick that out at the front by chain rule, so we end up with a n cos nt plus alpha. So that's our velocity. From there, we can go ahead and take the time derivative again, and that gives us our acceleration, right? Remember, dx dt, second derivative, d squared x dt squared, that's going to be our acceleration. So if we take the time derivative of that, we can bring the n out the front, right? Because derivative of nt plus alpha is still n, still linearly dependent, and so by chain rule, we end up with minus an squared, and derivative of cos is sine, so sine nt plus alpha, and so that's our acceleration expression. Now, if we look carefully at our acceleration expression, we see that we've got an sine nt plus alpha with an a, right? Or we can express this as, if we do a bit of rearranging, a bit of reshuffling effectively, minus n squared a sine nt plus alpha. Now, if we have a careful look at that, and we look at where have we seen that expression before, well, we've seen that expression right here. That was our position expression, right? And so we can say that our x double dot, our acceleration, is minus n squared x, right? And that's pretty cool because we can say that our acceleration is linearly proportional to our position, right? Because n is just a constant. So our acceleration is linearly proportional to the position. Now, we could go another path, and that is we start with our velocity expression, so we take that down there. So we have v equals an cos nt plus alpha, and if we square it, right, we get v squared equals a squared n squared cos squared nt plus alpha. Now, that looks like a bit of a mess, but the reason that's helpful is because we can use the Pythagorean identity, and we can express a squared n squared cos squared nt plus alpha as 1 minus sine squared nt plus alpha, and we've got a whole bunch of constants attached to it. So the cos squared is that, and we've got a constant of a squared and n squared attached to it, right? And so if we express that in that sense, we've got v squared equals to n squared times a squared minus a squared sine squared nt plus alpha. And so why is that useful? Well, if we look at this a squared minus a squared sine squared nt plus alpha, we see, well, where have we seen that before? That was our position function. And so we get v squared equals n squared times a squared minus x squared, right? And so that has some significance in terms of the physical sort of observation of simple harmonic motion, and we'll talk about that in a second. But those are our sort of very key distinct equations for simple harmonic motion. Obviously, the position, velocity, and acceleration sort of come from that. But acceleration, if something satisfies this equation here, that quite often means it's simple harmonic motion. If something satisfies this equation here, it means it's simple harmonic motion. Okay. And we have a similar sort of case for cos. We have a cos nt plus alpha, time derivative gives us velocity, minus an sine nt plus alpha. Second derivative with respect to time, we get x double dot equals minus an squared cos nt plus alpha. And so we get x double dot equals to minus n squared x. And squaring the velocity and so on gives us the same expressions. So it doesn't matter whether you start with sine or cos, you're going to end up with the same acceleration and velocity expressions in terms of position, like the relationship to position. You get, these two very useful results like we mentioned. And as we work through problems, you'll start to see patterns to understand which form, sine or cosine, is best to use in particular situations. But for a particle to be undergoing SHM, or simple harmonic motion, it needs to satisfy that. So that is, if you're asked to check whether a particle is undergoing simple harmonic motion, let's just say the sine or cosine function isn't very clearly built in, you could just test whether the second derivative with respect to time, that is the acceleration, is it proportional to minus n squared x. Now recall that Newton's formula for force gives us F equals ma, and so you can apply it to simple harmonic motion. You get F equals minus mn squared x. So that is, our force has to be proportional. Force has to be proportional to position, right? Because this mn squared, those are just constant, minus mn squared, those are just constants. So our force is proportional to position. If that's the case, that's a very clear example of simple harmonic motion when we're talking about springs. Springs the more you elongate them, the harder they pull, right? And it's actually a linearly proportional relationship. And so we end up with this being a very stock standard, perfect example of simple harmonic motion. Sometimes you might see pendulum cases, but the thing with pendulums, just the regular pendulums, like these ones that go back and forth, is that it's only simple harmonic motion for very small angles theta. Well, not very small, but for reasonably small angles theta. If you pass a certain point, then it becomes sort of quite bad in approximation. For simple harmonic motion is no longer a good approximation, but yeah. A very stock standard example is a block on a spring. Now, the negative sign, what it shows is that the force is directed towards the center of motion. If you, again, with the block on a spring, the further away you pull it from the center, right, the force is pulling it towards the center, not away from it. That's what the minus sign shows. Now, there are a few important results we can get from simple harmonic motion. That is, x dot equals 0 gives the magnitude of the greatest acceleration, and x double dot equals 0, i.e. at the center of motion, the speed is greatest, i.e. the velocity has its greatest or least value. It's sort of hard to describe in words, so here's a diagram. We have, at this point, right, so at acceleration 0, where the speed is the greatest, right, at this point here, so if, again, this is a particle on a, block on a spring or something, right, at the very center, the acceleration is 0, and the acceleration is greatest at the extreme points, where the speed is 0, right? So here and here, the acceleration is the greatest, but the velocity is 0. So if you think about the block on the spring case, when it approaches the maxima, it's going to have 0 velocity. When we're approaching the center, right, it's going to be going quite fast, but the acceleration is going to be 0. Why? Because the distance that the spring is compressed is 0. Because if you're right in the middle, the spring isn't compressed or expanded, and so therefore the sort of acceleration that it displays is 0. At the extremum, the acceleration is maximum because the spring is extended as maximum. So yeah, that sort of corresponds to our physical interpretation of simple harmonic motion as well. Okay, so simple harmonic motion about the point x equals c will involve a vertical translation of a trigonometric graph. The equations of motion for simple harmonic motion about the point x equals c can be written as so. Again, the c doesn't really do much other than shift our motion to the left or right or up or down or whatever. It's just there to show that the center is no longer 0, it's at some value. So let's just say now, if this is our axes, right, rather than having the center here at the origin, if, say, we're 1 meter across and now the spring or the particle oscillates between 0 and positive 2, well then our center of motion is going to be 1. That's all it shows. So that just means that it's going to be oscillating about this point. It's going to go to 2, back to 1, 0, 1, 2, and everything in between. So how does that change our displacement, velocity, and acceleration functions? Well, our displacement function has a little plus c added to the end. Our velocity function, that's just going to get rid of the c, right? Because if we take the derivative with respect to time of constant, it's just 0. The acceleration, again, if we take the derivative, doesn't really do much to it. But when we look at the acceleration and position relationship, we need to bring the x minus c, we need to bring the c onto this side in order to have that expression as being this one. And so that's where the x minus c comes from. And so in that case, it's just used to show that because it's still linearly proportional, right? The acceleration is still linearly proportional, but it's just the minus c is there to show that where at the center is no longer 0, it's at some point c. Because if we put in x equals c, that is, if we're looking at the point at which the particle is at the center, the acceleration is going to be 0. Because, again, spring on block example, the spring is no longer compressed or expanded or in tension, and therefore the acceleration is 0. So where x equals c, the center is that's the center of motion, sorry. A is the amplitude, 2 pi on n is the period, and alpha on n is the phase shift. let's do an example. This one is, I think, from 2022. Yep, 2022, I believe. So this is just an example of modeling with simple harmonic motion. It's not really too hard of a question in the sense that it's not something that involves a lot of heavy calculation. It's just something that involves modeling. But that's a really important skill to have, obviously, in the real world. If you're modeling something, sort of modeling comes first, and then your sort of analysis or the details. But modeling something accurately is very important. So the diagram shows two pistons of a single piston in the cylinder chamber of a motorcycle. The piston moves vertically in simple harmonic motion between the maximum of 0.17 meters and a minimum height of 0.05 meters. The mass of the piston is 0.8 kilograms, and the piston completes 40 cycles per second. That, remember, 40 cycles per second, that corresponds to a frequency, but the frequency can be related to the period. What is the resultant force on the piston in newtons that produces the maximum acceleration in the piston? Give your answer correct to the nearest newton. Okay, so first step is to come up with an expression for position, right? Is to come up with an expression for acceleration, or we can start from position and then get to acceleration. But if we can jump straight to acceleration, that's probably a bit faster. So let's look at what's happening in this case. What's our center of motion? Well, our center of motion is going to be the average between our minimum and our maximum. So our minimum is 0.17 and our minimum is 0.05 over 2. If you put that in the calculator, that is 0.11. That's our center. That's going to be somewhere about here-ish, I think. 0.11 meters. That's our center. And what does that mean in terms of our amplitude? Well, our amplitude is just going to be the distance from the center to either the minimum or the maximum. And so we end up with the amplitude is going to be, say, 0.17. We're going to take the maximum minus 0.11. So our amplitude is going to be 0.06 meters, right? And obviously that's going to be important in terms of when we're talking about acceleration equation and so on. Next thing to look at is the period. We're given the frequency is 40 cycles per second, or 40 hertz. So 40 cycles per second means that we're doing 40 sort of up and down motions each second, right? And so that means the time required for each sort of cycle is 1 on 40 seconds, or a 40th of a second, because if we have a 40th of a second and we can do 40 of those, that means, if we have each cycle takes a 40th of a second and we have 40 of those cycles, that's just going to mean 1 second. And therefore the period of each one must be 1/40th of a second, or in decimal form, 0.025 seconds. Okay, so that gives us the period. Why does that help with developing our equation? Well, that's going to help us get n. Because remember, 2 pi on n is the period, and hence we can go the other way and say that n is 2 pi over the period. And so we have 2 pi divided by 0.025. So that gives us 80 pi. Oops. 80 pi. And from there, what do we do? Well, we've got n, right? We've got the center of motion. Then let's try and fill in this equation. X double dot equals minus n squared x minus c. We have the details required, so we can say that's equal to minus 80 pi squared times x minus 0.11. And so our acceleration function becomes minus 80 squared, which is, let me do 80 squared, that's what, 6,400? 6,400 pi squared times x minus 0.11. Okay. Now, the question's asking for when the maximum acceleration occurs, the force when the maximum acceleration occurs. Clearly, maximum acceleration is going to correspond to the maximum force because F equals ma. And so, when does the maximum acceleration occur? Remember, maximum acceleration occurs at one of the extrema. Doesn't matter whether it's the minimum or the maximum. Either way, the maximum acceleration occurs when it's furthest from the center. And so let's take the maximum value. So x equals 0.17, for example, implies that x double dot. So if x equals 0.17, we get minus 6,400 pi squared times 0.17 minus 0.11. And what does that give us? So 6,400 times pi squared times 0.17 minus 0.11. That gives us 3789.928. 3789.928 meters per second squared. Again, the units, right? Units for acceleration, if we're dealing in SI units, is going to be meters per second squared. It's just going to be our unit for distance over our unit for time squared. So that means that our acceleration maximum is going to be about 3789.928 meters per second squared. And you can leave it in exact form if you'd like to. In this case, probably okay to round it because we're looking at sort of in mechanics, I would say rounding is fairly reasonable. Try and leave it in exact form if you can, but they shouldn't be too critical of rounding because it is mechanics in the end. Anyway, we have F equals ma, right? For our force, because we're asked for the force of the maximum acceleration, not just the maximum acceleration. There is a negative sign here, but we're interested in just the I guess they're just purely interested in the magnitude of the force, although the force is clearly going to be directed towards the center of motion, just with any simple harmonic motion question. So we get 0.8 kilograms was the mass of the piston times the acceleration, which is 3789.928. And so that means that our force is going to be approximately 0.8 times 3789.928, 3031 or 3031.942 newtons. That's our force. I'm sorry, 3 drop to 2. Yeah, 3 1. So force is approximately 3032 newtons. Because it says the nearest newton, so we're going to give it to the nearest newton, so 3032 newtons. That's our maximum force. Now, in terms of force, usually you want to specify direction, and the direction for simple harmonic motion is quite often just towards the center of motion. Okay, next question. The point P is 4 meters to the right of the origin. How are we doing for time? Okay. Because we are running sort of short on time, what we'll do is we'll do this one, and then we'll potentially, we'll see how we go with this one. So the point is 4 meters to the right of the origin on O on a straight line. Particle is released from rest at P and moves along the straight line in simple harmonic motion about O with period 8 pi seconds. After 2 pi seconds, another particle is released from rest at P, also moves along the straight line in simple harmonic motion about O with period 8 pi. Find when and where two particles first collide. So we're asked to find when, which is a time question, and where, which is a position question. Okay, now this is a bit of a tricky question, and so one of the very helpful things to do is draw a diagram. So if we draw a diagram, this is our line about which the oscillation occurs. This is O, this is the center of motion. This is P, and this is, we're going to call it Q. This is our sort of other extreme. The question says, particles released from rest at P and moves along the straight line in simple harmonic motion. So because it's released from rest at P, So because it's released from rest at P, the particle is here, right? And it's in simple harmonic motion about point O. And that means that it's going to take half the time to get here, right? And then half the time to get here. It says that the period of the particle is 8 pi, right? And so if the period of the particle is 8 pi, that means it's going to take 4 pi for sort of one back and one all the way this way, and then 4 pi for back, right? So that means it's going to take 2 pi to get to the center, and 2 pi to get to this extreme value. Right? So after that, 4 pi seconds has elapsed. Now this is, again, a bit tricky to see, but hopefully you can follow along with the logic. Then the question says that after 2 pi seconds, that is, when the particle is at P, right? When the particle is at O, after 2 pi seconds, another particle is released from rest at P, and also moves along the straight line in simple harmonic motion about O with period 8 pi seconds. That is, so you got two particles, identical setup, so again, spring and block system, identical spring, identical block, and they're in simple harmonic motion. The only thing that's different about them is that they're released at different times. We're asked to find when the two particles collide and where. There are two approaches to this question. One is to try and come up with equations of motion for both and try and look at what time it collides by equating them both. That's a perfectly valid solution, but there is a bit more of a clever way to do it. Sometimes in an exam situation, now I always emphasize this, sometimes in an exam situation you might not be able to see that, the sort of cleverer way. So if you've got the time to do so, brute force it, do it. But sometimes look for a cleverer way, and that could save you potentially 10 minutes worth of working. Okay, so we got 0 so from P to O is 2 pi seconds, O to Q is also 2 pi seconds. So by the time this particle, the red particle is, let's just say the starting one, the first particle, by the time it's at O, the second particle is released from P. So by the time the second particle arrives at O, the first particle's already arrived at Q. Right? Maybe I'll use a different color for that. Let's use yellow. So by the time the first particle is at Q, the second particle is at O, right? But the second particle is still moving this way. The first particle is still moving this way. And so they meet at the center, right? Because of symmetries, they meet at the center of the time period, not necessarily at the center of motion, right? In terms of the physical space, but center of the time periods. That means that they meet on the journey back of the Q particle and on the journey up of the particle that was at O. And so that means that because it takes 2 pi seconds to get here, halfway between them is going to be pi. So we get T equals to the first 2 pi, that is the 2 pi before the second particle was even released, plus the 2 pi at which point the second particle was at O, first particle was at Q, plus the time at which they meet, or like the sort of the midpoint time between the O and Q at which they meet is pi. And so maybe I won't use capital T, maybe I'll use little t. The point in time in which they collide is 5 pi seconds. Again, that might be a bit tricky to see in an exam situation or to reason that out. Try and explain it to yourself as well, because some of these questions, the logic behind them is a bit tricky, but try and sort of look through or imagine the situation. That I personally feel like it really helps. So you have 2 pi, suddenly the second particle gets released. This one gets to Q, this one gets to O, and then on the way back, or on the way up for the second particle, on the way back for the first particle, they meet in the middle, which is pi, so t equals to 5 pi seconds. Brute force method also works, by the way. Okay. So that answers the when question. We're now interested in the where question. That is where the two particles first collide. Because we're interested in the where question, we need to come up with an equation of motion for at least one of the particles. And I believe that the first one is probably going to be easier because we're not going to have to deal with some sort of phase shift. So we can say x equals to, what's the amplitude? Well, the amplitude is going to be, look back at the question, amplitude is going to be 4 meters because the point P is 4 meters from the origin, and we're centered about the origin, and so the amplitude is going to be 4. We can use a cos or sine, but because we're starting at the extremum, right? Sine starts at the origin, cos starts at 1, right? Because we're starting at the extremum, we're going to use cos because it's going to start at the higher point. Cos nt. Now, n in this case is dependent on the period. But we know that the period, t equals 2 pi on n, and so n is going to be 2 pi over the period, and so we end up with 2 pi divided by our period of 8 pi. So we get 1/4. And so we can say that x equals 1/4 t. That's our n. So nt. And now t is 5 pi, because that's the point in time which they collide, like we reasoned before. So we get x equals 4 cos 5 pi on 4 t. Sorry, 5 pi on 4, if we sub it in for t. And now if we evaluate that, cos 5 pi on 4 is minus 1/√2, right? And so we get 4 times, now minus 1/√2, we can say minus √2 on 2, right? Just by rationalizing the denominator. And so if that cancels, we get x equals to minus 2√2 meters. That's the point, that's the position at which they collide at t equals 5 pi. At t equals 5 pi, x equals to that. Again, not necessarily the center of O and Q, but it is the center in terms of time. So you have to be careful to differentiate between time and position and centers, because it's not necessarily symmetric about, it is symmetric about position, but not in terms of O and Q, or like in terms of how much time it requires, but it is symmetric in terms of time. Okay, we'll jump over this one just for the interest of time. This one shouldn't take too long. So we have a particle is moving along the x-axis and in simple harmonic motion. The displacement of the particle is x meters and velocity is v meters per second. Parabola below shows the function of x. Function of x. So v squared plotted against x. Part 1 asks for what values of x is the particle at rest. Not a trick question, very easy. Well, if the particle is at rest, v equals 0. V squared must therefore also be equal to 0. And when's that the case? At x equals 3 and x equals 7. So part 1, the answers are x equals 3, x equals 7. Okay. From there, we have... So from there, we have what is the maximum speed of the particle? Again, not a trick question, not a hard question. It's just v squared is 11. So if v squared is 11, maximum speed must be √11 meters per second. Part 3 is where it becomes a bit more interesting. The velocity v of the particle is given by the equation v squared equals minus n squared a squared minus x minus c squared. That's the equation that we derived before. We're asked for what n, a, and c are, and that's worth 3 marks. So first, we're going to look at what the center of motion is. So if the particle is at rest at 3 and 7, that means those are our extremum, right? Those are our extreme points. So the center must be the average of them. So 3 plus 7 is 10, divided by 2 is 5. So we know that the center, C, must be 5. Right? Easy as that. And then from there, we're asked to find what what A and N is. A is just corresponding to the amplitude. So if the center is 5, our extremes are 7 and 3. Amplitude must be 2, right? Because the distance from 5 to 7 is 2, and the distance from 5 to 3 is also 2. What's the value of A? What's the value of N? This is where things get a bit more interesting. This is when we're going to have to use potentially like the actual formula itself. So we're going to say v squared equals to n squared times 4 minus x minus 5 squared. Right? We're going to plug in v equals to v squared equals 11, right? That occurs at the center at x equals 5. So the second term in the brackets disappears. N squared times 4 is equal to 11. So you get n squared equals to 11 over 4. And so n must be root 11 on 2. And that's our n. So we get a equals 2, c equals 5, n equals root 11 on 2. Easy as that. I'll also skip over this one. The solutions are in the slides if you're interested for this multiple choice question. The reason I put this here is also a bit of a warning. Sometimes multiple choice questions can seem deceptively simple. Like for 1 mark, you might not expect that amount of work, but as you can see, it does involve a bit of work to get the answer out. Sometimes trial and error does work, but not always. Okay, now jumping into some resisted motion. Most of our questions from now on will involve particles that have some mass, and to account for this, we're going to use Newton's second law. So we're going to get so sum of forces equals to mass times acceleration. Now, force is a vector, acceleration is a vector, but we can consider them in terms of components. So we consider them in terms of x, y, and z components. So that helps to come up with like a net force expression for each dimension, effectively. So to build a differential equation to solve these motion questions, we need to sum up all the forces involved and then apply Newton's second law. Most forces should be given to you, or at least described in the question, and you may have to draw free body diagrams to resolve forces. That's very important, and it's even something that turns up in the extension 1 syllabus when we were talking about vectors. Drawing free body diagrams, it feels like more of a physics thing, but it's very important to do with mechanics, because mechanics is effectively physics topic, just with calculus in it. I enjoy it. When a particle moves through a medium, it is subjected to resistance. The resistance acts in the opposite direction to the motion. E.g., if the particle falls vertically, the resistance acts upwards. If the particle is projected upwards, the resistance acts downwards. Now, that seems a bit wordy, but effectively what it's saying is if you throw a ball upwards, right, the ball experiences a drag in the opposite direction to motion, so it's pulling it downwards alongside gravity. If you drop a ball, say, from the top of a building, the air resistance acts opposite it, and therefore it acts against gravity. The resistance is pretty much always opposite the velocity. The drag and friction is pretty much opposite motion. Some cases, I think the majority of cases is the same. Resistance forces, acting to oppose the direction of motion. When an object moves horizontally, we can avoid gravity. Instead, we look at resistive forces such as friction, which acts in the opposite directions of velocity. And these are just a couple of integrals which may turn up, which are quite useful, so I just threw them in there. So if a particle of mass m is fired upwards with initial velocity v through a resisting medium under the influence of gravity, g, let y be the height of the particle above the point of projection, and time t, the only forces acting on the particle are the resistive force and the weight, thus the net force is that, and we can come up with an acceleration expression. The sort of very important thing to do with these sort of questions is to define a clear axis system. So or a sign convention. So if we're going to assume positive is upwards, Then if we're looking at the forces, we've got gravity downwards, right? So it's going to be minus mg. And we've got air resistance also downwards, minus mkv to the power of n. And usually n is usually 1 or 2, depending on the situation or depending on the particular problem. So the net force is going to be the gravity, which is pulling down, so minus mg, minus mkvn, which is also pulling down, equals to my dot, double dot, sorry, mass times acceleration in the y direction, and you can do a bit of cancellation, and that will give you y dot equals minus g plus kv to the n. Okay. When a particle travels vertically through a medium, only two forces act on the particle, force due to gravity and the resistance motion. Typically, it is found that the resistance is proportional to the power of speed, v, thus the resistance equals minus mkv to the n for some constants. Sometimes it's not mass dependent, so you won't see an m in there, but most resistance, air resistance in particular, is proportional to the square of the velocity, but yeah, it's some power of n. Sometimes it's 1, sometimes it's 2 usually. Sometimes 3, very rarely though. Yeah. But in the question they will definitely specify, so you don't have to sort of come up with it yourself. The only forces acting on the particles are gravity and air resistance. So this is in the case of, again, upwards is positive. This is in the case of, sorry, if we take downwards as positive, my mistake. If we take downwards as positive, in this case, and the particle is launched upwards, particle is falling downwards in this case, we get mg acting downwards, but because the particle is falling downwards, air resistance acts in the opposite direction, so we get minus mkv to n. And so the net force is going to be your downwards gravity, which is going to be positive because we assume downwards is positive, minus mkvn, which is upwards. And it's a negative because we assume downwards is negative. And that's going to say mass times acceleration is that. We can divide through by mass, and we end up with that expression here. And this is a differential equation which you've potentially seen some of in extension 1. So yeah, not too hard. Here is a example of particle with resistance. Let me just have a quick look in terms of time. Shouldn't be too bad. We have quite a few examples, but I think this one's definitely worth going through. It's a 4 marker, so it's not something that's it's going to involve potentially a bit of work, but hopefully not too much. Sometimes 4 markers are nice to you, and there'll be ones where there's just a little trick in there that you have to use in order to get the answer. Sometimes it can be grueling and a lot of work. Sometimes a very small little trick can really simplify the problem. So you get 10, 1 minus kv squared. That's the acceleration. And we're asked to find the velocity of the particle after 5 seconds. So we're looking for a velocity-time relationship. So let's start. Let's start with, again, we're looking for velocity and time. So what version of acceleration should we use? We should use dv dt. So we get dv dt equals to 10 times 1 minus kv squared. And if we reciprocate it, we end up with dt dv equals to 1 over 10 times 1 minus k squared v squared. If we expand it. Now, I won't go through the partial fractions in detail, but in order to integrate this function, you're going to have to use partial fractions. And so I'm just going to jump to the partial fractions because I'm sure you would have done at least a few of them in the further integration topic. So I'm just going to jump through that. Now, this isn't in a form that we can easily integrate like that. So we're going to have to use a bit of factorization. And that's one of the reasons that they gave it to us in 1 minus kv. Sorry, that should be outside kv squared like that. The reason they gave it to us is in order for us to identify that it's a squared minus b squared form, so difference of 2 squares. Yeah, and so we get 1 over 1 minus kv, 1 plus kv, And so using partial fractions, that should show us that that's equal to 1 over 10 integral of 1 over 1 minus kv plus 1 over 1 plus kv dv. Okay. From there, we can integrate this. These are just ln functions, so we end up with 1 over 10 times, that should be a half. Now, the partial fractions also ends up with a half, so this should be 1 over 20, that should be 1 over 20. And we can pull out the k when we integrate them, so we get ln 1 minus kv minus, 1 plus kv ln 1 minus kv, just by using integrals, and then we just reshuffled them, so we put the positive at the front, negative at the bottom, negative on the other side. And so from there, we can express that as t equals to 1 on 20k ln 1 plus 2k, 1 plus kv, 1 minus kv, right? And so when and we've got the plus c as well, because it's an indefinite integral. Now, in order to evaluate the plus c, again, we look back at the question, look for initial conditions, and that is that particle starts from rest. So that means that t equals 0, v equals 0. So if that's the case, we get 0 equals to 1 on 20k ln k times 0, so 1 over 1, which is 1, plus c. ln 1 is just 0, so we end up with c equals 0. And therefore our expression becomes t equals to 1 on 20k ln 1 plus kv of 1 minus kv. Right? Now, they've actually given us the value for k, but before we sub it in, we're looking for v in terms of t, right? We could, at this point, try and rearrange for v, but I think it might be actually quicker in order to solve for v after we sub in the numbers. So we have at t equals 5, we end up with, and we can sub in our t as well, we end up with, and we can bring the 20k up, so we get 20k times 5 equals to ln 1 plus kv, 1 minus kv. And so we end up with 20 times, our k value was 0.01, times 5 equals to ln 1 plus kv over 1 minus kv. And nicely enough, the left-hand side, if you evaluate that in your calculator, turns out to be 1. So we end up with ln 1 plus kv over 1 minus kv equals 1. And so if we exponentiate both sides, we end up with 1 plus kv equals to 1 plus kv over 1 minus kv, is equal to e. And again, if we sub in k equals 0.01, doing a bit of rearranging, and I'll skip the rearranging steps, you end up with v equals to 100 e minus 1 e plus 1, which is 46.2 meters per second. So yeah, for 4 marks, bit of work, but not terrible. Okay. We will potentially skip the following question. It's an inclined plane question, not terribly difficult, but it is something that actually is required in the Extension 1 syllabus to be able to do. That is to resolve forces on an inclined plane. This one is just with the forces in with a resistance force as well. So you've got the gravity force pulling it down, and you've also got a resistance force. I encourage you to do this one in your own time as well. And part 2 is the slide down as constant speed. Okay, that's just solving for. So we've got the resultant force. We can look for the acceleration and looking for the specific value of v in which the constant speed, which is acceleration, is 0. Yep. Okay. This is an interesting question. This is from the 2020 HSC Extension 2 paper. We do have quite a few practice questions. This one again is resolving forces. So I think what I want to do is quickly run through this one, which is forces on the object, because it's not something that's quite often sort of really emphasized enough, in my opinion. So we've got, when we look at the forces on the system, now the proper way to do this is to look at the forces on each individual mass and try and compare that. Although that's not, that's more of a physics approach. Although I think it's equally valid, and I think that's a better approach. But even NASA has suggested sort of doing the approach in which we use the sort of looking at the forces on the system as an entire system, if that makes sense. So we have the 4 mg, right, pulling it downwards. And let's just say anything that assists the motion downwards is positive. Anything that resists the motion is negative. Now, that's not the best sign convention to use because sometimes it's hard to tell what's assisting motion, what's resisting motion. But in this case, it's not too complex of the system, so we can do that. So we can say that the net force is equal to 4 mg, right? That's assisting motion. But then we've got resistance on that block. So we can say minus kV. And then we've got a 2 mg. Is that assisting motion or is that opposing motion? Well, if 4 mg is moving downwards, the 2 mg is sort of counterweighting on the other side and it's pulling downwards. And so we get minus 2 mg, right? And then that block also resists, also experiences an air resistance, hence the minus kV. And so if we use that and simplify a bit, we get 2 mg minus 2 kV, right? And that's equal to mass times acceleration. The mass here, the net mass is 4m plus 2m, so 6m times a. Again, it's looking at the forces on the entire system rather than individual blocks, but the individual block approach should still work. And so we end up with the acceleration. If we divide through by 6m, is going to be mg minus kv, doing a bit of simplification, over 3m as required, or gm. That's the way they like to write it. Okay. We can choose. You can choose either one of these. I reckon. Looking at the time, we can probably do the second one, I think. But they're quite similar, but the second one's a bit more interesting. So I have particle A of unit mass traveling horizontally through a viscous medium. When t equals 0, the particle is at point O with initial speed u. The resistance on particle A due to a medium is kv squared, where v is the velocity of the particle at time t and k is a positive constant. When t equals 0, a second particle B of equal mass is projected vertically upwards. So we've got a unit mass particle that is initially having speed u, particle A, yeah, and it experiences both a gravitational force and a resistance due to the medium. The resistance on particle B is kw squared, where w is the velocity of the particle. At time t, the acceleration due to gravity is g. Now show that the velocity v of the particle A is given by 1 over v kt plus 1 over u. Now this is a good question because it combines both horizontal and vertical resisted motion, and so we can sort of get both covered in one shot. So first thing to do, draw a diagram. So we have particle A that we're interested in first, and that one's traveling horizontally, right? So that's our velocity. And if we look at the net force, and the sign convention that I'm going to use is to the right is positive. And therefore we have the force of resistance acting to the left of kV squared. So if we look at the net force, which equals to mass times acceleration, mx double dot, and I can use x double dot here because we're talking about the horizontal axis, and x-axis is usually our horizontal axis. Get minus kV squared is equal to mass times the acceleration. Now the mass here is 1 because it's a unit mass. So yeah, x double dot is minus kV squared. Okay, and here we have an acceleration and a velocity relationship. So which form of velocity should we use? Well, if we look at what we're trying to prove in the question, if we bring up the slides quickly, but look at what we're trying to prove. We're trying to prove a time expression. So we got 1 on v equals kt plus 1 on u. So if that's the case, then we want a velocity time relationship. So we're going to use dv dt equals minus kv squared. And so if we reciprocate both sides, we end up with dt on dv equals to minus 1 on kv squared. And so we end up with time as being the integral of minus 1 on kv squared. And that's just going to be minus 1 on k, integral of v to the minus 2 dv. So using power rule, we end up with minus 1 on k times minus 2 v to minus 1 plus c. Oh, sorry, my mistake. Shouldn't be there. That should be v to the minus 1 plus c. And so we end up with t equals to minus 1 on kv plus c. Now, let's go ahead and multiply through by k. And it doesn't really matter what we do with the constant because it's still, again, a constant. So we get kt equals to minus 1 on v plus c. And in order to evaluate what c is, we need some sort of initial condition, right? And that's where the t equals 0, v equals u comes in. So that's our initial velocity. T equals 0, v equals u. So we have 0 equals to minus 1 on u plus c. So that must mean c equals to... Oh, sorry. This negative here cancels. That should be positive, positive. Yep. Positive 1 on u, so c equals to negative 1 on u. And so our expression becomes kt equals 1 on v plus 1 on u. Right? Yeah. Okay. So that's part 1. Part 2, by considering the velocity w of the particle b, show that t equals to 1 on root gk, tan inverse, so and so, so and so. Okay, now this particle b is a case of vertical resisted motion. So if we look at the axis as being, if we take the sign convention as being upwards as being positive, so if we take upwards as positive, and we look at the forces that are acting on the system, we've got minus g, right, gravity pulling it down, minus mg effectively, but remember mass is 1, so it doesn't really matter. Minus mg, and we've got a resistance of kw squared, right, which is also pulling it downwards. Because it's launched upwards, the resistance is also pulling it downwards, minus kw squared. Okay, and so we get acceleration is equal to, well, mass times acceleration, but mass is a unit, so we get minus k omega squared or w squared minus mg, and so you get acceleration equals to kw squared minus g because the mass is 1. And so our expression becomes dw dt equals to minus kw squared minus g. Right. Now the reason that we use our velocity time relationship, that is our dv dt sort of relation, is because we've got t equals something something in terms of u and w, right? And that means that we have a velocity time relationship. So let's go ahead and integrate this. Let's take the reciprocal, dt on dw equals to minus 1 on g plus kw squared. We can then integrate. Time equals to the integral minus the integral of 1 on g plus kw squared dw. Now this may seem like a tricky integral, but if we write it in this form, if we pull out a factor of 1 on k, maybe it becomes a bit more obvious what this is. It's g on k plus w squared. Well, if we have something plus something squared in the denominator, that usually indicates we've got some sort of trig, right? Trig function, or inverse trig function. In this case, it's tan inverse, and so that the thing inside the brackets for tan inverse must be the square root of g on k. So that implies that we get t equals to minus 1 on k, minus 1 on k times root k on g, because the reciprocal of the inside brackets has to be at the front. Tan inverse w root k over g plus c. Right, and we can put the c outside if we'd like. It doesn't really matter. And so we end up with the expression, if we do a bit of cancellation with this k and the k out inside, we get t equals to minus 1 on root gk, right? Because we've got a half a power on the top, whole power on the bottom, so we can turn that into a half a power on the bottom. Tan inverse w square root k on g plus c. Right. Now to evaluate the constant here, we're going to have to use some initial condition. So looking back at the problem, we're told that at t equals 0, second particle is projected vertically upwards from O with the same initial speed u. So that means at t equals 0, v equals u, or w equals u in this case. So that means that we end up with c equals to 1 on root gk tan inverse u, because we replaced the w with a u, square root k on g plus c. Sorry, the c we moved on the other side. And therefore, our new expression therefore becomes t equals to 1 on root gk. Now this is a longish expression, but just have to be careful with things. Tan inverse u root k on g minus 1 on root gk tan inverse w on root kg. Okay, and so our t expression, if we pull out a 1 on root gk, now this is pretty much what we're looking for, so I'm just cleaning it up and into the form that they've specifically asked for. Tan inverse of u square root k on g minus tan inverse W square root K on G. And so we're done. Okay, so that was part 2, 3 marks, not too bad. Show that part 3 says show that the velocity of the particle A when particle B is at rest is given by that. Okay, it's an interesting question. So when particle B is at rest, we're asked to find the velocity of particle A, right? So if particle B is at rest, that means that W equals 0, right? So if W equals 0, let's see what that gives us in terms of our time expression. So if W equals 0, our time expression becomes 1 on root gk, tan inverse u root kg, that's just a constant, remember, that's all constants, minus tan inverse of 0 times square root k on g. Now tan inverse of 0, that's 0, hence this term cancels out, and so we are left with t equals 1 on root kg, or root gk, tan inverse of u times root k over g, right? And we're asked for the velocity of particle A when particle B is at rest. So we got the when, that is what time that occurs. Now we're looking for what is the velocity of particle A. Well, our velocity of particle A, we came up with an expression for that in part 1, which is 1 on V equals to kt plus 1 on u. And so subbing in the t value that we just got there, you get k times 1 on root gk, tan inverse of u times root k over g plus 1 on u, and doing a bit of combining fraction, or this is an expression for it, but yeah, actually, that is the expression that we're looking for. So we get 1 on v equals to 1 on u, so if we pull the constant out first, and then we got root k on g, so that means that we've got k over square root of gk, so that means we got root k on g, because we got a whole power, half power on the bottom, so that means half power on top, tan inverse u root kg. Okay. Finally, part 4. Hence, if v is very large, hence if u is very large, explain why v equals 2 over pi root g on k. Because we have a expression here in terms of u, right? And we're looking at when u is really large, that just means that we're looking for what happens as u approaches infinity. So if u approaches infinity, this term here, 1 on u, becomes really, really small. That becomes negligible and 0. Root k on g, tan inverse of, in pretty much a really, really big number times some constant, is still going to be a really, really big number. Now, tan inverse of a really, really big number is just going to be pi on 2, right? So we end up with 1 on v equals to square root of k on g times pi on 2. And if you're ever in doubt, have a look at the tan inverse function graph, and you'll see that as x goes to x positive or negative infinity, positive infinity approaches pi on 2, negative infinity approaches negative pi on 2. And so taking the reciprocal, so we get v equals to square root g on k times 2 over pi. Or the way that they wanted it was v equals to, now they shouldn't be that concerned about which order you write it, but it's better to just write it in the way that they're looking for. Okay. So, moving on. Again, the slides do have a few questions in there for you guys to try on your own. They are pulled from past HSC papers, but definitely recommend giving it a shot yourself before you actually look at the solutions. Okay. So to find terminal velocity, just a little side note before we end up on resisted motion. To find terminal velocity, that's just what happens as a limit as t goes to infinity of v of t. Just like the position, right? We took the limit as t goes to infinity. Similarly, we take a limit as t goes to infinity for velocity to see what the terminal velocity is, or what the limiting velocity is, sometimes it's called. It's pretty much, if you're in perfectly vertical resisted motion, we end up with So if you have the net forces being mg this way and kv squared that way, or kv this way, dependent on that, we get mg minus kv squared, if we take downwards as positive, equals to mass times acceleration. And if we set acceleration equals 0, that is, when the velocity approaches the terminal velocity, the acceleration becomes slower and slower, right? Because it's approaching that velocity and it's almost hit that maximum velocity. It can't go any faster than that. That means that the acceleration is approaching 0, and so we end up with mg equals kv squared, and so we get v equals to the square root of mg on k, or if it's a unit mass, or if it's not a square expression, we get mg equals to mkv, for example. Then we end up with the m's cancel, so you have v equals g on k, the limiting velocity. And if you were to graph it, you should see something like this. Approaches that value, that's our terminal velocity. Okay, so it looks like about 50 in this case. Meters per second. Okay, now into projectile motion. We don't have too much time ahead of us, but I will try and get through majority of content. Not too much content, new stuff. Try and get through as much of one of the particular problems as possible. Okay, so this is just a GeoGebra simulation of projectile motion. There are plenty of really good projectile motion simulations out there, and so you can have a play around with it. It sort of helps you build up sort of a physical sort of feel for how projectile motion works. This one actually takes into account air resistance as well. The red one is one with resistance, the blue one is one without resistance. So clearly, taking into account resistance is important, particularly in cases where you've got high resistance or you've got a small mass, or if you're shooting a bullet or something, obviously air resistance, it's relatively important. But let's just say you're throwing a dart, for example, air resistance is less so important as compared to, let's just say, a piece of paper or something that's falling to the ground. Much more significant effect of air resistance. Okay, so in 4 unit, the projectile motion questions are a continuation of the ones covered in 3 unit. However, can get arguably quite challenging. There is no new content in the topic, just harder questions. Sometimes you might see sort of a mixture of 3-dimensional vectors and projectile motion. Unlikely, but has happened before in past trial papers, and I'm not sure in the HSC, but in trial papers I have seen that. So that can happen. You can get harder questions which involve air resistance. Now, there's only a very select type of air resistance cases which you can get, because anything beyond that cannot be solved using extension 2 method. You're going to have to use some differential equation solving methods, and so because that's the case, where there's only a select type of resistance question that can give you, not every type of question. Okay. Here is a question from 2020 HSC. If you have a careful look at this question, you'll see that pretty much it's purely built on extension 1 content. There's pretty much not that much extension 2 content involved, or pretty much none in that question, because deriving the equations, part 1, is something that's stock standard extension 1 question, right? You just do it step by step like you would always. Part 2 is deriving the Cartesian equation, which again is something that you would have seen in extension 1. And part 3 is just sort of an inequality question, not too hard. So this was actually from 2020 HSC, and for 8 marks from that, I would say it was pretty generous. Okay, so this is another HSC question. This one's actually trickier. This one's interesting, so it involves a bit more vectors involved. But again, it's still built on extension 1 content. It's probably wouldn't expect to see this level of difficulty in extension 1 exam, but still possible to be done with extension 1 techniques. Okay, let's try and run through this question as quick as possible. So we've got a particle that's projected from the origin with initial velocity u at an angle of theta to the horizontal. The particle lands at x equals r on the x-axis. The acceleration vector is given by acceleration equals 0 minus g, where g is the acceleration due to gravity. And don't prove this. Show that the position vector of the particle r of t is that. Now, that's 3 marks. That's your stock standard derivation. I won't spend too much time on that, right? Because it's just deriving the equations. So we'll jump to question. Oops, sorry, it's this one. So we've got a particle which is projected from the origin with initial speed u at an angle of theta. The positive x-axis and lands on the ground. We're shown that this is the equation. We're asked not to prove it. We're asked for some value of theta. There will be 2 times during the flight where the particle's position vector, r of t, is perpendicular to the velocity vector, r dot of t. We're asked to find what value of theta this occurs and justify that both times occur during the time of flight. Okay. So it is a bit of a tricky question, but we'll try and get through it as quick as we can. So we'll start off with our position equation, r of t, and I'll probably skip some of the algebra and leave that for you guys to do, because mainly I want to demonstrate some of the key ideas in this question and some of the sort of jumps that we make in the logic, which can be a bit tricky to see. So minus gt squared on 2 plus ut sine theta. So that was our position equation. And so our velocity expression, our velocity vector expression, our dot of t, is just going to be the time derivative of the x and y components. So we get u cos theta minus gt plus u sine theta. Right? And so we're asked for the point at which they're perpendicular, the position and the velocity vectors. So that must mean that the dot product, remember when we talk about perpendicular vectors, quite often we refer to the dot product. R of t times r dot of t, like the dot product between r of t and r dot of t, has to be 0, right? So we get, we'll sub it in, so we get ut cos theta minus gt squared on 2 plus ut sine theta dotted with u cos theta minus gt plus u sine theta. And doing a bit of algebra, and I'm going to skip some of the steps, we're going to end up with t on 2 times g squared t squared minus 3 ugt sine theta plus 2u squared. And if they're perpendicular, right, if these 2 vectors are perpendicular. Now, to get this expression, by the way, you just use your regular dot product. You multiply the x components, multiply the y components, add them together. If they're perpendicular, this thing has to be equal to 0. And so looking at that factorization, t cannot be equal to 0, right? Because if t equals 0, then that means that we're talking about the position and the velocity at the origin. Now, of course, because it's the origin, all points are effectively perpendicular to it, but that's sort of like the trivial case. We're interested in this term here. Now, if there are 2 points in time which this is true, right, that means that this here, this thing inside the brackets, the square brackets, has to have 2 solutions. And this is a quadratic, right? And if a quadratic has 2 solutions, what does that mean? Well, then we're interested in the discriminant, right? And so we've got g squared t squared minus 3u gt. And this discriminant trick is, it's not really a trick, but it's something that turns up quite often, is if you've got a quadratic and you're interested in not really what the solutions are, but how many solutions there are, then you want to sort of look at the discriminant, right? So the discriminant in this case is, after you do a bit of cleaning up, is actually u squared g squared times sine squared theta, minus g squared 9 sine squared theta, minus g has to be greater than 0. Now, u squared, g squared, those are just two constants squared, so that is positive, so we can get rid of them. So you get 9 sine squared theta minus g has to be greater than 0. Now, if that's the case, then we can say that, if we clean it up again, we get, sorry, that should be an 8, not a g. That's my mistake. Yeah. So if we clean it up and do a bit of rearranging, we get sine squared theta has to be greater than 8 over 9. Or if we square root both sides, sine theta has to be greater than root 8 over 3. Now we take the positive solution because theta is between 0 and pi on 2, so sine must be positive, and you can write a little note there that for the sake of mathematical sort of rigorousness, mathematical rigor, I think. And so theta, if you sine inverse that, has to be greater than 1.23. And we can take that value because it's an increasing function within that 0 to pi on 2 domain. Okay, so theta equals 1.23. Theta has to be greater than 1.23. What does that mean? Well, we assume that the discriminant has to be greater than 0, meaning two solutions. So if theta is greater than 1.23, we have two solutions in which the time is perpendicular to the position, where the velocity vector is perpendicular to the position vector. And that's only if theta is greater than 1.23. But it has to be less than pi on 2, of course, because that's our assumption. And if you convert that 1.23 radians, and if you convert that to degrees, it's about 17.52 degrees. Okay, so that solves the find the values of theta part of that question. Now we ask for the times, justifying that both times occur during this flight. We're not asked for what times they occur, but we're asked to justify that they occur during the time of flight. Now, to do that, we're going to have to solve this quadratic, right? And if we try and solve this quadratic, we're going to end up with, pretty much using quadratic formula, you can end up with t equals, now this is after some cleanup, so I'm going to skip over those steps, but I, again, strongly encourage you guys to put the actual algebra in as an exercise. Sine theta plus or minus square root of 9 sine squared theta minus 8 right. Okay. And in order to have this time as being within the time of flight, right, we need to have this time as being positive, right? So we want to try and show that this time is positive, which means that it doesn't matter whether we take the plus or the minus case, right? It must be positive. Now, if we take the plus case, obviously it's going to be positive because sine theta is positive. The thing under the square root is going to give us a positive. And so square rooting a number is going to give us a positive if we take the positive root. But what happens if we take the negative root? Is that going to give us a negative value? If so, then it's outside our time of flight, right? Because remember, the model doesn't know anything about the actual sort of the physics of the situation. The model only knows about it's a parabola, right? So if we end up with a negative time, it just means that we've got an issue there. It's not in our time of flight. Okay, so to show that it's a positive value, what we're going to have to look at is this 9 sine squared theta minus 8. Is that greater than 3 sine theta is what we want to try and show. Well, clearly 9 sine squared theta minus 8 is less than 9 sine squared theta, right? Because if we subtract something, if we subtract an 8, that has to be smaller. And that is equal to 3 sine theta squared. So effectively, we have something that's smaller than 3 sine theta squared subtracted from 3 sine theta. Well, something that's smaller than 3 sine theta squared so 9 sine squared theta minus 8, right, is smaller than 3 sine theta squared. And once we square root that, we're effectively subtracting something that's smaller than 3 sine theta from 3 sine theta. So that means that we're going to end up with a positive value. So 3 sine theta is bigger than whatever value of theta we put in. 3 sine theta is bigger than this one. Well, between theta is 1.23 and 90. 3 sine theta is going to be bigger, so that when we take the negative and we subtract this value here from 3 sine theta, we're going to end up with a positive t. So t has to be greater than 0 for both cases. Now, obviously, in the exam situation, you'd write out a bit of an explanation there, but that just means both points occur after the projectile lands. After the projectile is launched, and in order to check whether the projectile it occurs when it lands, consider the points on the trajectory below the projectile. So we've got two cases here. We've got one that it occurs, one of the points in time occurs before the time of launch, and the other case is after the time of landing. But if you think about the path of the projectile, we have, this is the path, and our position vector is going to be something like that, right? That's r of t. And our velocity vector is going to be parallel to the path, or sort of tangent to the path, r dot of t. Now, both r of t and r dot of t, they point into the fourth quadrant, right? That means that, like this one, this r of t, that's in the fourth quadrant. The r of t, the r dot of t is in the fourth quadrant. R of t is in the fourth quadrant. So that means that if we take the dot product, that must give us the angles between them is less than 90. It doesn't matter how you draw the system. That's always going to be the case. And so that must mean that the 2 points that occur here cannot be giving us 0, right? Because if it's greater than 90, obviously it's not going to give us 0. So that means that both cases occur when t is greater than 0, but t is less than the time of flight. Hence, the 2 points occur during the time of flight. Now, you have to write that out in a bit of an argument, but for the sake of time, I'm going to skip that, but that sort of gives you the crux of what the case is. Now, jumping into exam technique in hopefully the last 3 minutes or so. So one of the biggest things is to make sure that you develop an understanding of each topic, or understand the workings of each topic. Use a visual or geometric approach rather than a purely algebraic approach, if it's possible. Sometimes you're just going to have to brute force through and work through the algebra. But sometimes it can simplify things, especially with complex numbers, for example. If you can visualize the situation quite in terms of rotations and dilations, that quite often can simplify things. You also want to practice as much as possible. Build up mathematical foresight, that is, be able to see, okay, if I do this, will this work? What form of acceleration am I supposed to use? That's one of the big things. Developing a mathematical foresight in terms of what you want to try and improve, what you've got given, how do you get there? Is there, try and come up with different approaches. If you're stuck on practicing problems, rather than reading the solution straight away, see if you can get a hint to complete the rest of the question, whether from your teacher or from your tutor or from, maybe just a peek, I guess. But try not to look at the solution all the way, right? Because that's not super helpful. Try and give yourself a hint and work from there, because sometimes it's that small jump in that logic that is what gets you stuck, particularly for extension 2. So trying to sort of get that, build up that intuition is quite important. And when practicing, ensure that you try timed papers. So do untimed papers in terms of like older papers, I would recommend, so that you can do them sort of topic by topic, and then try timed papers for the more recent ones, especially because you've got the 2020, 21, 22, 23, all exams that are there for you to do with the new syllabus. And exam time management is really important, and you need to try and sort of experiment with different strategies, see which one works best for you. Reading time, not too much. There really isn't too much time, so it's not really intended for you to properly attempt all the problems, but it is for brainstorming ideas. So again, if you build up that mathematical foresight, once you see a problem, you can sort of come up with, okay, this is my pathway to solve this problem. And so you need to try and sort of, that's what you need to be trying to do in exam, in reading time. Sometimes people suggest doing multiple choice. I wouldn't recommend that. I would really recommend going towards, the end, right, where you've got some of the harder questions, trying to come up with like a pathway to do them, because that's probably what's going to take you more time than the multiple choice. Okay. Sometimes algebra is inevitable, especially for proofs or mechanics, but can potentially occur in any of the topics, integration, for example. You still need to fight through it for the marks, though. Sometimes you can simplify, like I said, with a bit of geometrical intuition or sometimes a bit of physical intuition, but not always. And so you need to just work through it. Series trigonometric identities, they also turn up out of nowhere sometimes, so you need to be familiar with the series formulas from advanced and trig identities from extension 1. Sometimes they can really simplify your equations, and also never be scared to experiment. Sometimes you need to try a method. If it doesn't work out, try another one. Don't waste too much time on a single method, but yeah. And most importantly, have fun. These are really important topics, really useful topics. I enjoyed them, and Extension 2 is a really enjoyable course if you actually sit down and play around with topics and look at, especially mechanics, I personally found really enjoyable. But yeah, any questions? If not, that's it for today. Thank you guys for coming. See you guys next time.